In this video, we'll finish up Chapter 1 at the second section on equivalence relations and partitions. Again, still mostly a review. You probably encountered these for the first time in a discrete math class or a foundations class. But just to review, an equivalence relation on a set X is a relation which technically is a subset of the cross product of the set X with itself, such that the relation has these three properties, that it's reflexive, symmetric, and transitive. Reflexive is just that every element is related to itself. Sometimes you would write this as just x or x like that. If x, y, or x is related to y is how you would read this. We could again write it this way, x related to y. Implies that y is also related to x, so that's the symmetric property. So maybe I'll write this version of it as well. And then the transitive property is if x is related to y and y is related to a third element z, then x and z, or x is related to z. So this is potentially a one-way relationship. So when I say, I can't say x and z are related, it would be x related to z. So in this notation, it would be if x is related to y and, we'll use the symbol for and in logic, y related to z, this implies that x is related to z. If all three of these are true, then we say that the relation is an equivalence relation, and that it partitions, or as a result of being an equivalence relation, it partitions the set X into disjoint subsets of X, whose union is the whole set, and every element, or pairs of elements in one of those parts are all related to each other. So we'll first see a couple of examples that aren't quite equivalence relations. So we'll see that they satisfy two of the properties, but not a third. And then we'll finally see an example that satisfies all three. So the first relationship is just x less than or equal to y. And whenever you describe an equivalence relation, there should be some domain that you're working on, because sometimes it might be an equivalence relation under one domain and not under another domain. So here we're working with the real numbers. And so you can see how like this notation maybe makes sense. So if you replace that r with this symbol, then it makes more sense to write it that way. So the r sort of is the variable for whatever symbol you're putting in between. So let's test each property. So let's first inquire about whether or not this is reflexive. So in other words, we're asking, is x less than or equal to x? And this is, of course, true. Remember, the less than or equal to symbol is a or statement. It's less than or equal to. And x is equal to x, so it is less than or equal to. So it gets a check mark for reflexive. What about symmetric? Well, by its nature, the less than symbol is kind of a one-way thing. So it's certainly not going to be symmetric. And if you want to show something is not a particular property, then you just provide a counterexample. You provide a couple of specific members of your set where it doesn't hold. So in this case, we could say 1 is less than or equal to 2, but 2 is not less than or equal to 1. So that makes it not symmetric. And of course, there's many other examples, but you just have to come up with one to show that the property doesn't hold. And then finally for transitive, is it transitive? It turns out to be transitive. Of course, if x is less than or equal to y and y is less than or equal to z, then certainly x is less than or equal to z. If you were to plot this on a number line, you'd have x less than or equal to y, and then y less than or equal to z. So certainly x is further down the number line than z is. So this does imply that x is less than or equal to z. So we get a check mark there. So we got 2 out of 3. So it's not an equivalence relation, but it does have a couple of its properties. Our next example, the absolute value of x minus y is less than or equal to 4. Again, working in the real numbers. So let's first ask about reflexive. So is x minus x, if the x and y were the same number, is that an absolute value less than or equal to 4? Well, of course, its absolute value is 0, and that is certainly less than or equal to 4, so it gets a check mark for reflexive. Is it symmetric? So if x minus y in absolute value is less than or equal to 4, is it also true for the absolute value of y minus x? Well, this is true because the absolute value of x minus y is the same as the absolute value of y minus x. The difference between subtracting in a different order is just a difference in their sign, but the absolute value removes that sign, so these are equal to each other. So if one of them is less than or equal to 4, then the other one is also less than or equal to 4. And then finally, again, I already gave away that this is going to fail in one and not in the other two, so it's certainly going to, or it should fail transitivity here. So we have to come up with some values of x, y, and z, where it's true for x and y and z, but not for x and z. So here I came up with 1 and 4. The difference between 1 and 4 in absolute value is less than or equal to 4. And the difference between, say, 4 and 7 is less than or equal to 4. So this is acting as the x and y and z. And so if I inquire about 1 and 7, the absolute value, so I'll put a but here, but the absolute value of 1 minus 7 is 6, so that's not less than or equal to 4. So it does not pass transitivity. Next example, m times n is greater than 0. Both m and n are in the integers this time, so this is our domain, the integers. So is this reflexive? So to be reflexive, it has to be true for every element in the domain. And so this is true for most elements. N squared or m squared is usually greater than 0, but it's not true for 0 itself. So 0 times 0 is not greater than 0. So it does fail being reflexive. What about the other two? Is it symmetric? Well, the symmetry here comes from the fact that multiplication is commutative. So m times n is the same as n times m. So if one of them is greater than 0, then the other one being equal to it would also be greater than 0. Check mark there. And then finally, transitivity. Here I'll do kind of a little bit of a proof here. So suppose m times n is greater than 0 and n times p is greater than 0. Notice that that implies that every value here has to be non-zero, because if any of them were 0, then you would get 0 and not something greater than 0. So this implies that in particular, so all of them are, but in particular n is greater than 0, or sorry, not equal to 0. It certainly can be negative. But we need that for the proof. So what I'm going to do is multiply these two together. If I take mn and multiply it by np, well, I'm supposing they're both positive, so the product of two positive numbers is again positive. And now I get mn squared p. And since n is not 0, I'm allowed to divide by n. And n squared would have to be a positive number. So n is not 0. It could be a negative number, but when I square it, I get something positive. So I can divide both sides of my inequality by n squared and not change the direction of the inequality. So notice I can't do that if I tried to divide both sides by m. It's not allowed because, or I wouldn't know what would happen because m could be positive or negative, and so it could switch the direction. But I can divide by n squared. So I get MP is greater than 0, which is what I wanted, because that's like, if I think of this as the x and y and z, so x is related to y, y related to z, the m and p are like the x and z. So it does pass transitivity. This is probably the first one that we've seen so far that we could amend in a way to make it an equivalence relation. So let's suppose we change things. We did m n greater than 0 as our relationship, but we do it in z without 0, which is what we sometimes call z star. So this is just non-zero integers. Notice that was the only real problem here. So now it becomes reflexive, and it's still symmetric and transitive. So this is an equivalence relation. And so that means it should partition the domain, z star, into what we call equivalence classes. So z star, I should be able to partition it into subsets where every element in each of the subsets are related to each other. So here it just splits it into two subsets. You have the negative numbers and the positive numbers. So the negative integers are all related to each other, because if you multiply two negative numbers together, you get something positive. All the positive numbers are related to each other, because if you multiply any two positive numbers, you get something positive. But none of these are related to each other. And I took 0 out already, so 0 doesn't appear here anyway. And our last example is finally going to be an equivalence relation without any amending like we did in the last one. So m and n are related to each other if they're congruent mod 6. So let's first remind ourselves what that means. M congruent to n mod 6 means that the difference between m and n is divisible by 6, so we could write it this way. Or we could say m, the difference between m and n, is a multiple of 6. So is equal to 6 times k for some k in the integers. We'll probably take this as our definition as we go forward. So first let's ask about reflexive. So is a number related to itself mod 6 or congruent to itself mod 6? So since m minus itself is 0, well, that is a multiple of 6. So it's 6 times 0. So that would imply that m is congruent to m mod 6, and the modulus wouldn't really matter here. Actually, in all these, in the proof of all three of these, we'll see the modulus doesn't really matter, but it's nice to have one just for the example. But this would be true for any modulus. So for symmetric, we assume that it goes one way and prove that it goes the other way. So suppose m is congruent to n mod 6. So our goal is to show that n is congruent to m mod 6. So the other way around. So of course, by definition, this means the difference between, the specific difference, m minus n, is a multiple of 6 for some k in the integers. And we kind of seen this before. If I switch the direction, you just get the negative, or you could think of multiplying both sides of this equation by a negative. You get n minus m would be negative 6k, or 6 times negative k. And negative k is still an integer. So that would imply that n is congruent to m mod 6. So, oh yeah, didn't do check marks. So it's both symmetric and reflexive. What about transitive? So suppose I'll use the p like we did in the last one for the third value. So suppose M is congruent to N mod 6 and N is congruent to P mod 6. So let's use the definition for each of these. This means M minus N is a multiple of 6 and N minus P is a multiple of 6, let's say L. And so these are for some K and L in the integers. Now what's nice here is I can add these two equations together and get exactly what I want, because I want M to be congruent to P, so I want M minus P somehow. And I'll get that exactly if I just add these two equations together. So let's do this sort of slowly. So M minus N plus N minus P is equal to the sum of the other sides, 6K plus 6L. And then, of course, the n's cancel out. So I do get the M minus P that I want, and I can factor out a 6 here. And K plus L is an integer. So that would mean M is congruent to P mod 6. So it gets the check mark for transitive as well. Now, equivalence classes here are a little bit more interesting. Let's make a big circle. So this is all the integers. So I want to put all the elements that are related to each other in the same subset. So for example, so we could just start off with 0 and say, what's related to 0? Well, every other multiple of 6 is related to 0, including negatives. Those are all related to each other. And then ask what's related to 1, or what is congruent to 1 mod 6. So again, we're asking, what values that when I subtract 1 gives me a multiple of 6. So certainly 7 would do that. 7 minus 1 is 6. 13 minus 1 is 12, which is a multiple of 6, and so on. So just continually adding 6 or subtracting 6 going the other way. So all those are related to each other. And we keep going in the same pattern. What's related to 2? Well, 8 would be related to 2. 14, you can kind of see what's going on here. Just increasing each of these by 1. Minus 4, and so on this way. So we'll just finish this up. So 3, 9, 15, negative 3, 4, 10, 16, all these numbers. And then finally 5, 11, 17, minus 1. Forgot the minus 2 here. And that should include every integer. So it partitioned the integers into 6 sets, each of which are sets that are equivalent to each other. We generally say, call each of these by some representative. So we'd say this is the congruence class for 0, for 1, congruence class for 2, 3, 4, and 5. Or I could say that this is the elements that are congruent to 4 mod 6. Okay, so that's it for chapter 1. In the next video, we'll start into chapter 2, which is still a review chapter. The real algebra starts in chapter 3.